Well, this is just informal discussion till everybody's in here. So, any questions on the subject? What? Everything. Okay, well, you know what? You guys should stop and ask more things as you go along, because there is just no way you could get all of this. And it's a little strange. And only by talking about it, you will at least know what's going on. There's no way to make it reasonable. It's not a reasonable world out there. I can only tell you what it is. I take that view when I teach quantum mechanics. Just tell the rules and say this is what happened, this is how we calculate things. And whether you like the formalism or not is not my concern. And the fact that it doesn't look like daily life, also not my concern, because this is not daily life. Strange things happen. But you have to keep me informed on how much you're following and what you're understanding at any stage. Don't wait for this to end, because it's not something where you can go on the last day and figure everything out. And I will try to repeat at every stage what has gone up to that point, because the whole thing is only a few lectures, maybe 6 or so. I can afford to go back every time at the beginning. But I know that it makes sense to me because I've seen it, and I don't know how it sounds to you. I have no clue. You know that, and so you have to speak up. You can ask any question you want, and I will try to answer you if it's within the realm of possibility. Okay. So what have I said so far? So let me summarize, even if you never came to a last lecture. Here is what you should know about the last lecture. Okay? Here's what I said. First thing I said is, everything is really particles. All things. Electrons, photons, protons, neutrons, they are all particles. So let there be no doubt about that. By that I mean, if one of them hits your face, like an electron, you will feel it in only one tiny region, one spot. Electron dumps all its charge, all its momentum, all its energy to one little part of your face. So there's nothing wave-like about that. It's not like getting hit by a boxing glove, which can hit your whole face. Electron hits one dot. Okay? Or if it's an electron detecting screen, only one pixel is hit by the electron. And into that pixel is given all the charge, all the momentum, all the energy of that electron. That's exactly what particles do. So when you encounter an electron, it is simply a particle. So where does the problem come in? Where does the quantum mechanics come in? It comes in when you do the famous double slit experiment. That's the key. The entire quantum mystery is in the double slit. Part of the resolution is in the double slit, but the rest are a little more difficult, and I'll try to tell you. First, I want to tell you what goes wrong with Newtonian mechanics. After all, if everything is a particle, what's the big deal? What's the problem? The double slit experiment is a problem. That's what puts the nail on the coffin for Newtonian physics, and here it is in basic version. You got two slits. By the way, I'm going to call the particle the electron. They're all doing the same thing. So what applies to one applies to all of them. There is a source like an electron gun that emits electrons. Like in the old days, televisions had the electron gun. And the gun emits electrons, they go hit the screen, they make a little dot, and then the dot moves around, and you see your favorite show. Okay, this is the electron gun. And the electron gun has been engineered to send electrons of a definite momentum. That you can get by accelerating the electrons over a definite potential, and that gain of so many electron volts will turn into kinetic energy. As for direction, if this gun is really far away to the left, in principle 1 mile, then the only way electrons are going to go 1 mile and hit the screen if they're all basically moving the horizontal direction. Then you put a row of detectors in the back, which will detect electrons. Then this is slit 1 and this is slit 2. You block slit 1. In fact, let me say the following thing. What do we really know when we do the experiment? Once in a while, this gun will emit an electron. And we know it's emitted the electron because it'll recoil one way, just like a gun, rifle. It'll recoil. That's when we know the electron left. Then we don't know anything, and suddenly one of these guys, it says click. That means electrons arrived here. This is what we really know. Everything else you say about the electron is conjecture at this point. You know it was here, you know it was there. Question is, what was it doing in between? Now, if you say, look, things cannot go from here to there except by following some path. I don't know what path it is. Maybe if it's an ordinary particle like Newtonian particle, it'll take some straight line, hit that slit, or go through that slit and arrive here. So you might say, I don't know the trajectory, but it's got to be some trajectory. Maybe like that. Or maybe like that. So the electron takes some path, and you can label the path as either through slit 1 or through slit 2. Okay, now here is the problem. Suppose I do the experiment with slit 2 blocked, so you cannot even get through this one, and I sit at a certain location for a certain amount of time, maybe 1 hour, and I see how many electrons come, and I get 5 electrons with only one slit open. And if I move that observation point, I get some pattern, pretty dull, looking like that, and I'm going to call it I1. That's the count as a function of position up and down that wall of detectors. Then I repeat the experiment with this guy closed and that guy open, and I get another count. Looks like that. Now, I'm going to pick a location. Now, these are not drawn to scale or anything, so I'm not responsible for any of that. Maybe I'll at least show you one thing which is pretty important. This graph will be big in front of the second slit, so which is somewhere here. It will look like that. So I get I1 when 1 is open, and I get I2 when 2 is open. This is I1, this is I2. Now I'm going to open the 2 slits, and I'm going to pick a particular location. It doesn't happen everywhere. I'm going to pick one location called X. But I used to get 5 electrons per hour with one thing open, and 5 electrons per hour with the second thing open. Now I want to open both and ask, what will I get? In Newtonian mechanics, there's only one possible answer to that question, and that is 10. Because if you got 5 this way, and you got 5 that way, and you open both, whoever is going this way will keep going that way, whoever is going this way will keep going this way. They will add up to give you 10. Now, I told you, some people may say, well, maybe it's not 10, because with both slits open, maybe someone from here can collide with someone from there, and how do you know that will happen? So I'm saying, do the experiment with such a feeble beam of electron. There's only one electron at a time in the whole lab. It's not going to collide with itself. Then you wait long enough, and you have to get 5 plus 5 equals 10. And what I'm telling you is, if you go to the location marked X, where you got 5 with each one open, when you open both, you will get 0. You don't get anything. That is a great mystery. That is the end of Newtonian physics. And I told you that something like that never happens in your daily life. I gave an example with machine guns. It's a machine gun. This is a concrete wall with 2 holes in it. And there's some target here, you. And then you see how many are coming through this and how many are coming through that. Then you go there and you wait. And both are open. Somehow nothing comes. With the second hole in the wall, you are safe. With one hole in the wall, you're not safe. That can never happen with bullets. So these electrons are not following any path. Because the minute you commit yourself to saying it follows one path, either through this one or that, you cannot avoid the fact, with both of them open, the intensity with 1 plus 2 has to be equal to I1 plus I2. That's the Newtonian prediction. And I1 plus I2 gives you 5 plus 5 equal to 10 here, and you get 0. In other places, instead of 10, you will get 20. Some places you get more, but the more dramatic thing is where you get less, where you get nothing. Therefore, you abandon the notion that electrons have any trajectories. You don't want to abandon it, but you have to, because that assumption, which is very reasonable, just doesn't agree with experiment. Then you say, okay, what should I do? Newtonian mechanics is wrong. What's going to take its place? To find that, you have to move away from this x and move up and down this row here and see what you get. And I think I told you what you get. You get a pattern that looks like this. So the real I1 plus 2 looks like this, got ups and downs and ups and downs. And let's say these downs really correspond to 0. That means nobody comes here, a lot of them come here, no one comes here, few come here, and so on. That's what you find. I'm just telling you what happens when you do the experiment. So you put yourself in the place of a person who did the experiment. You thought of moving away from that point x. When you plot it, it makes no sense in the language of particles. But this is such a familiar pattern. If you're a trained physicist, which you guys are, you will say, hey, this reminds me of just wave interference with water waves or sound waves or any waves. Obviously, there's some wavelength. The minute you give me wavelength and a slit separation, I can calculate this pattern. D sine theta equal lambda and whatnot. And from that sine theta, where you get a minimum or a maximum, and if there's a certain separation to the screen, you can find the precise location of these maxima and minima. Or given the maxima and minima, you can work back and find the wavelength. And the wavelength happens to be some number called h bar, which is 10 to the minus 34 joule seconds, divided by the momentum. P is the momentum. In other words, you find that if you send more energetic electrons, accelerate them through bigger voltage, you increase the P, lambda goes down, the pattern gets squeezed. You slow down the electrons, P reduces, lambda increases, the pattern spreads out, and the dependence on momentum is inversely proportional to momentum, and you fool around and find out the coefficient of proportionality, which people used to call h in the old days, is now written as 2 pi times an h bar. It doesn't matter, it's some constant, and the number is 10 to the minus 34. So you can successfully reproduce this pattern. But what does it tell you about what's going on? What good is that pattern? The pattern tells you that if you repeat the experiment with this electron gun 1,000,000 times or 1,000,000,000 times, and you plotted the histogram patiently, the histogram will eventually fill out and take this shape. So this wave is not the wave associated with the huge stream of electrons. A single electron in the lab is controlled by this wave. You need a whole wave for one electron. So it's obviously not a wave of electrons. It's not a wave of charge like a wave of water. It's the mathematical function, and you are drawn to it because the only way you know how to get this wiggly graph is to take something with definite wavelength and let it interfere. So you're forced to think about this wave. And the intensity of the wave, the brightness, if you like, or the square of its height, gives you what? Gives you the graph you will get if you repeat the experiment many times. And what does it mean for an individual trial? What does it mean for the 1,000,000 plus 1th electron? But for the 1,000,000 plus 1th electron, it gives you the odds of where it will land on that screen. Okay? You can never tell exactly where it will be. You can tell what the odds are. And the only way to test a statistical theory is to do the experiment many times. And if you do it, it works. And it seems to work for everything. For electrons, for protons, for photons, whatever it is, the wavelength and momentum are connected in this fashion. So this wave is forced upon us, and it gives you the odds of finding the electron somewhere. And we say that the probability, I'll be a little more precise in a minute on what I mean by the probability to find it at a location x. But let's just say, if you draw the graph of size square, wherever it is big, probability is large. Wherever it is small, probability is small. Wherever it is 0, probability is 0. So that seems to be a function whose amplitude or whose square gives you the probability. That function is called the wave function, and we know it exists because it's the only way to calculate the result of this experiment. Once you tell me that the fate of a particle is controlled by a wave, you're immediately led to some other conclusions. So I'm going to tell you what they are. First conclusion is this. If I make a single slit, let's call this the x direction, let's call this the y direction, and I'm sending a bunch of particles in the x direction with some momentum p naught. In Newtonian mechanics, I can manufacture for you an electron of known momentum and known position, or known to arbitrary accuracy. If delta x is the uncertainty in my position and delta p is the uncertainty in momentum, I can make each of them as small as I like. So here's an actual practical way to prepare such a state. If I say, give me an electron of known position, known momentum, here's what I will do. I'll take a slit with a very tiny hole in it. The width of that hole is d. And whoever comes out on the other side, what can I say about that particle? Its position has an uncertainty of order d. Because if it was not, I'm sorry, delta y now, because this is the y direction, right? Anything who came out of the hole right after it had to have a y position was known to within d. It could have come anywhere within the slit, but that's it. So prepared for you. That's how you filter out electrons at definite position. And you can make delta y as small as you like by making the slit as thin as you like. What about its momentum? It had a momentum p0 in the x direction, no momentum in the y direction. Therefore, py was strictly 0, no uncertainty. Delta py is 0, and the fellow I catch here is moving horizontally with that momentum p naught, whose y position is within d, and I can make the d as small as I like. This is Newtonian physics. But we have now learned that the fate of the particle is not in its own hands. It's contained in this wave. So what should I do in this context to find out what it will do? Any idea what I should do to find out what will happen in this experiment, given what we learned? Yep. Right, but how will I calculate what will happen in this experiment? What will decide? Yes?
You can assume that the two edges of the hole are the two holes in the double slit experiment.
Yeah. This is one hole, and a light beam is coming from the left. I mean, the wave is coming from the left. And if the particle has momentum p naught, it's got some wavelength, which is 2 pi h bar over p naught. But if you want to know what will happen on the other side of the slit, I have to find the fate of that wave. Yeah, you can put a screen, but what will I see on the screen? Will the wave just hit this region? You know it will spread out from diffraction. I told you the light will spread out. This is the main, there are tiny wiggles we ignore. At this point, where you get most of the action, that angle, theta, satisfies d sine theta equals lambda. This is just wave theory. That's when you can pair up the points in the slit in the hole into things shifting, differing by half a wavelength. So for every one I can find a partner that cancels it. You will get 0 here. Beyond that, you may get a few more rises, but it's pretty much dead outside this cone. That means you will observe this particle anywhere in this angular width. Now, a particle cannot go from this slit to there unless it had a momentum, which had a component in the y direction. You cannot get there from here unless you have y momentum. So the y momentum is uncertain to within that cone. So what's the uncertainty in the y momentum? For a vector of length p naught, when it gets shifted by an angle delta theta or by an angle theta, it is just p naught times theta. Or if you like, precisely p naught times sine theta. But p naught sine theta is controlled by d sine theta equals lambda. So this is lambda over d. But lambda is 2 pi h bar over p naught times d. You cancel that. You find delta py times d is equal to 2 pi h bar. But that means delta py delta y is roughly, forget the 2 pi, of order h bar. So you should understand this much completely without any doubt. If the future of the particle, the fate of the particle, is controlled by the wave, you try to narrow the location of the particle by making the hole smaller and smaller, the wave fans out more and more. That's just wave theory. People knew this about waves hundreds of years back. What is novel is that this wave is going to tell you where the particle will end up. This wave is going to control the odds of where the particle will end up. And the odds are pretty much concentrated in this cone, not of zero opening angle, but an angle theta, so that d sine theta equals lambda. Lambda, in turn, is connected to the momentum of the particle. This is where the uncertainty principle comes in. What Heisenberg said is, you had in your mind the classical notion that you can have a particle of known position and known momentum. Let me see you produce that particle. So you try to do it by putting a slit and catching guys with a very narrow range in y, but now you find out that the momentum gets broader and broader. And that's the result of the wave associated with the particle. It was not in the Newtonian picture. Yes?
Why with a single slit like you've drawn there, do you get those little wiggles and then has the outside wiggle?
You mean why would it have those wiggles?
Yeah.
Okay, so if I look at the single slit, I can think of made of many little point sources, right? In the forward direction, if you go very far, so that you treat them as roughly parallel, they are all in step. You get a big maximum. In another direction, where this difference is lambda, d sine theta equals lambda, this guy and this guy are differing by lambda over 2.
So you're assuming the slit is large enough to produce that?
These are little mathematical dots inside the slit. You know, when you make a slit, every point on the slit looks like a source of light, a point source of light. They are not really light bulbs, but if you make any hole in the wall and light comes through, that hole looks like it's a source of light. I'm taking every point on the hole to be a source of light. And what I'm saying is there is a direction in which it will cancel, but if you go a little further out, it won't cancel completely. This is the direction for perfect cancellation, where I can pair them, this one with this one, that one with that one, and so on. They pair to give 0. But if you move further up, you no longer cancel completely, but you don't add perfectly either, so things will get better, then they'll get worse again, and better and worse, and so on. So that's the origin of that pattern. Yeah?
So you're just saying, like, basically the first minimum, after that, everything's pretty small.
Yeah. For a single slit diffraction, the big thing in the middle is pretty much all you have. It's not like a double slit experiment with 2 holes where you get many times the pattern. That's because, let's understand why that is true. Here, if these two differ by 1 wavelength, they don't differ at all. I can find another angle where they differ by 2 wavelengths. They don't differ at all. There's only 2 sources, so you can engineer them to differ by either 1 wavelength or 2 wavelengths or 3 wavelengths. Here, in a single slit, each point is like a source of light. You got them all to agree. You can get them to agree only in the forward direction. In any other direction, you can get them to neutralize each other, but never for perfect reinforcement. So you cannot get it more than, this is the only real maximum here. Everything else is tiny. Yes?
Why can't you do the same trick with the double slit, where each of the one slits has its own?
No, in double slit, what's happening is in double slit, the number d I used in double slit was not the size of a slit, but the spacing between the slit. Okay? So there I took the size of every slit to be vanishingly small. That means the light coming out of this slit spreads out completely in all directions. Okay? It's as if this packet became that broad. Likewise, the light from this one we are still in the first maximum of that slit. So you got to understand, in a single slit experiment of diffraction, the slit size is what you're varying. In a double slit experiment, the slit is taken to be mathematically point-like, so it's fans out completely. It's the interference between those 2 point sources that you're adding. They can add and cancel many, many times as you move along this line. Okay, so what we learn is that It's when you combine waves and particles and go back and forth that you run into the situation. So you cannot make a state of perfect momentum. By the way, I said one thing, I thought about it, which is incorrect, which is in the microscope. I said if you want to locate the position of an electron in a microscope, so take a microscope with some opening, and the electron is somewhere on this line. And I said you're shining light down here. It hits the electron, but it goes in through the slit by spreading out. So the photon that came in goes into the eyepiece with a certain uncertainty in its final angle. That means we know the incoming momentum, but we don't know the outgoing momentum of the photon, because the lens picks up everything inside that cone. That means we don't know how much momentum it gave to the electron. It gives an indefinite amount of momentum to the electron. Therefore, the x momentum of the electron is uncertain by that little shape, the conical shape of the momentum. And if you do the uncertainty principle argument, you'll again find delta x, delta p is h bar. Now, what I don't like about my experimental setup is that I had the incoming light also coming from inside this inside the microscope, but that means incoming light, when it comes through this hole here, will itself spread. Then it'll hit this guy, and that'll go to the aperture, that'll spread some more. This uncertainty in incoming momentum is unnecessary. We can do better than that, because in other words, when the light is picked up, it is picked up by this tiny hole. There's no reason it should also come from the tiny hole. It can come from a source far away, say, on the other side, so that it is a well-defined direction. It's not diffracting at all. It's not. So I wanted to come in through a very broad hole, so it's got well-defined direction. So the light here has known momentum. It hits the electron and goes into the microscope. It is the final momentum of the photon I don't know. And I cannot make it better. If I make it better, I got to open this eyepiece a lot. If I open the eyepiece a lot, I don't know where I caught this guy. So again, the problem between taking a very tiny eyepiece so that if I see a flicker, I know the electron was in front of it, but the light coming from the reflected electron fans out more and more. Okay, so anyway, this is the uncertainty principle. And the uncertainty principle told us something very interesting. I asked you, what can be the function here that produces this interference pattern in the double slit? We know the wavelength. Wavelength was 2 pi h bar over p. And you know from basic physics that a function like cosine 2 pi x over lambda has got wavelength lambda. So let's put in the formula for lambda here. You get cosine 2 pi x. Lambda is 2 pi h bar over p. Cancel the 2 pi's. You get a cosine px over h bar. That function, when you throw it at a double slit, will form two little wavelets, and they will interfere. They'll produce an interference pattern of the type you want. Do you understand that the experiment only showed you there's a wavelength? Did not tell you what the actual function is. That's very, very important. When Young did the experiment with the double slit, he found the oscillations and he could read off the wavelength, just geometry. But he didn't know what was oscillating. He didn't know there's an electric and magnetic field underneath all of that. But you can always read out the wavelength without knowing what's going on. Likewise, we have the wavelength. We know it comes from a function with a well-defined wavelength, so I make my first guess to be this function. But I told you what was wrong with this choice. Do you guys remember that? I said this function violates the uncertainty principle. The uncertainty principle says if you know the position to an accuracy delta x, and if you know the momentum to accuracy delta p, the product must be at least as big as h bar times some number of order 1. We have taken the particles to have well-defined momentum. If they have well-defined momentum, delta p is 0. Delta p is 0, delta x is infinity. Now, I told you the square of the wave function is the probability to find it somewhere, and you have no idea where it is. In other words, a particle of perfectly known momentum has totally unknown position. So the probability should look flat. Psi squared should look flat. But the psi squared due to cosine, of course, does this. It prefers some locations to another, but you're not supposed to have any preference for any x. So we have a problem. How do I put in a wavelength into a function whose square is flat? That's the problem we have. When you think about it, you realize your trigonometric functions will not do the trick. If they have a wavelength, their square is not flat. The square is also oscillating. But then what came to the rescue is the following function, not a cosine, but a e to the ip x over h bar rather than cosine xp over h bar. Look at this function. This function, I've told you many, many times, if you don't have complex numbers, you're definitely going to have trouble. It looks like a vector of length L and angle theta, which is px over h bar. As you vary x, this x changes and this will rotate around. But as it rotates, the amplitude of this complex number, absolute value of psi square, which is psi times psi star, which is a, I'm taking a to be real here, so a star is this, times e to the ipx over h bar, times e to the minus ipx over h bar. That cancels out, you just get a square. In other words, the complex number describing the wave function changes in phase but not in amplitude. It's the amplitude that gives the probability. Now, there is no problem with this guy having a wavelength because this oscillates in x. Its real part and imaginary part both oscillate, but the square of the real plus imaginary square is 1. That's why the amplitude doesn't change. So we are driven now to the very interesting result that the wave function for a particle of definite momentum p is this. So this is a very important lesson. Let me label this wave function by label p to tell you, hey, I'm not talking about any old wave function. This guy has a definite momentum p. Its wave function looks like e to the ipx over h bar times any number a you want in front of it. That's a very important thing to know. This is called a plane wave, and a plane wave with the p right where it is describes a particle of momentum p in quantum mechanics. And I told you particles of momentum p are everywhere. Every machine produces them. Every accelerator produces them. And if you want to describe them in quantum mechanics, you have to know complex numbers. There's just no way you can get a real answer to our predicament. It's complex. So that's roughly where I left you. And I want to remind you of a few other things, this further discussion of the result we have. Okay? The discussion is, if the world is really this messed up at the microscopic level, why do I think it's the world I see in the macroscopic level? Where are all these oscillations? Why is it that when there's a concrete wall, making another hole is bad for me? They're not good. Why do all these things happen? Why do I think particles have definite momentum and position? Why do I think